Tonight, we're going to explore something you can see in our night sky, visible with your naked eye if you know where to look: the Andromeda Galaxy. You've probably heard it's the nearest large galaxy to us, the one that's going to collide with the Milky Way in a few billion years. But here's what most people miss. Andromeda isn't just another galaxy. It's more than twice the diameter of the Milky Way, contains roughly 1 trillion stars, and sits 2.5 million light-years away. By the end of tonight, you're going to understand not just how big Andromeda is, but what that size actually means for our understanding of cosmic scale, for the fate of our galaxy, and for the very nature of the universe itself. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Look up on a clear, dark night in autumn or winter if you're in the northern hemisphere. Find the constellation Cassiopeia, the distinctive W shape in the sky. From there, trace a line to the constellation Andromeda. There, in that constellation, you'll see a faint smudge of light. That smudge is the Andromeda Galaxy, also called Messier 31 or M31. It's the most distant object you can see with your naked eye. And when I say distant, I need you to understand what that actually means. That faint smudge of light you're seeing isn't something close by like a star or planet. It's not even in our solar system or anywhere near it. That light left Andromeda 2.5 million years ago. 2.5 million years. When that light began its journey toward Earth, humans didn't exist yet. At 186,000 miles per second, crossing the vast emptiness between galaxies for longer than our species has existed. And it's only just now reaching your eyes. That should be your first clue about the scale we're dealing with. But let's start building this understanding properly, from the ground up, because to really grasp how big Andromeda is, we need context. We need to understand what we're comparing it to. Let's start with Earth. Earth is about 7,900 miles in diameter. That's big enough that if you stood at one point on the surface, you couldn't see even a tiny fraction of the whole planet. The curvature of Earth limits your view to maybe a few dozen miles on a clear day. Earth is enormous from a human perspective. It takes hours to fly across it, days to sail around it. But in cosmic terms, Earth is tiny, infinitesimally small. Let's zoom out to the solar system. The Sun, our star, is about 864,000 miles in diameter. That's about 109 times wider than Earth. If the Sun were hollow, you could fit more than 1 million Earths inside it. That's already a scale that's hard to comprehend. 1 million Earths. But the solar system is so much bigger than just the Sun. Neptune, the outermost planet, orbits at an average distance of about 2.8 billion miles from the Sun. If you were to travel from the Sun to Neptune at the speed of light, it would take you about 4 hours, and Neptune is still inside the solar system. Beyond Neptune lies the Kuiper Belt, a region of icy objects that extends out to about 7.5 billion miles from the Sun. Beyond that is the Oort cloud, a spherical shell of comets that marks the true edge of the Sun's gravitational influence. The Oort cloud extends out to about 9 trillion miles from the Sun, maybe as far as 19 trillion miles. At this distance, we're talking about roughly 2 light-years, give or take. So our solar system, from the Sun to the outer edge of the Oort cloud, is about 2 light-years across. That's the neighborhood we live in. Now let's zoom out further. The nearest star to our Sun is Proxima Centauri, part of the Alpha Centauri star system. Proxima Centauri is about 4.24 light-years away. 4.24 light-years. That's about 25 trillion miles. If you wanted to travel from Earth to Proxima Centauri, at the speed of our fastest spacecraft, Voyager 1, which moves at about 38,000 miles per hour. The journey would take roughly 70,000 years. And Proxima Centauri is our nearest neighbor. The next nearest star system, Barnard's star, is about 6 light-years away. Sirius, the brightest star in our night sky, is 8.6 light-years away. These distances are already so vast that they defy normal human intuition. We can say the numbers, but truly comprehending them is nearly impossible. But we're just getting started. Our Sun is located in a region of the Milky Way galaxy called the Orion Spur, a minor spiral arm. We're about 26,000 light-years from the center of the galaxy, 26,000 light-years. That's about 153 quadrillion miles, a number so large it becomes meaningless. But let's put it in perspective. If you wanted to travel from Earth to the center of the Milky Way at the speed of light, it would take you 26,000 years. The light we see from the galactic center today left there before humans developed agriculture, before we built cities, before recorded history even began. The Milky Way galaxy itself is a massive structure. It's a barred spiral galaxy, meaning it has a central bar-shaped structure with spiral arms extending from the ends of the bar. The Milky Way is about 100,000 light-years in diameter. From one edge of the galaxy to the other, light takes 100,000 years to travel. The galaxy contains between 200 billion and 400 billion stars, though estimates vary. Each of those stars could have its own system of planets, moons, asteroids, and comets. The Milky Way also contains vast clouds of gas and dust, the raw material from which new stars form. And threading through all of this is dark matter, the mysterious substance that makes up about 85% of all matter in the universe. Dark matter doesn't emit, absorb, or reflect light, so we can't see it directly. But we can detect its presence through its gravitational effects on visible matter. The Milky Way's total mass, including dark matter, is estimated at about 1.5 trillion times the mass of the Sun. That's the galaxy we live in. That's our cosmic home. And it's absolutely enormous by any standard we can comprehend. But now, let's talk about Andromeda. The Andromeda Galaxy is the nearest large galaxy to the Milky Way. It sits about 2.5 million light-years away. 2.5 million light-years. That's about 14.7 sextillion miles. A sextillion is a 1 with 21 zeros after it. To put this in perspective, if the Milky Way were the size of a dinner plate, Andromeda would be another dinner plate about 20 feet away. That's how far apart our two galaxies are on a cosmic scale. Not very far at all. In fact, in cosmic terms, Andromeda is practically our neighbor. But despite being our neighbor, the distance is still incomprehensibly vast. If you could travel at the speed of light, the fastest speed anything can travel according to the laws of physics, it would take you 2.5 million years to reach Andromeda. And if you wanted to travel there at the speed of our fastest spacecraft, Voyager 1, the journey would take about 69 billion years. That's about 5 times the current age of the entire universe. So even though Andromeda is our closest large galactic neighbor, it's still impossibly far away. Now let's talk about Andromeda's size. The Andromeda Galaxy is a spiral galaxy, like the Milky Way, but it's bigger. Quite a bit bigger. Andromeda is about 220,000 light-years in diameter. That's more than twice the diameter of the Milky Way. If you place the Milky Way and Andromeda side by side, Andromeda would be noticeably larger, stretching out beyond the Milky Way's edges on all sides. But size, in terms of diameter, is only one way to measure a galaxy. What about the number of stars? The Andromeda Galaxy contains approximately 1 trillion stars. 1 trillion. That's 1,000 billion. By comparison, The Milky Way contains somewhere between 200 billion and 400 billion stars, so Andromeda has roughly 2 to 5 times as many stars as the Milky Way. Imagine this: 1 trillion stars, each one potentially with its own system of planets, each planet potentially with its own moons. The sheer number of worlds in Andromeda is beyond comprehension. If you wanted to count every star in Andromeda, and you could count 1 star per second without stopping, it would take you about 32,000 years to count them all. And that's assuming you never sleep, never take breaks, and can somehow keep track of which stars you've already counted. It's impossible, of course. The number is just too large for the human mind to truly grasp. But let's try to build some intuition for what 1 trillion stars actually means. If every star in Andromeda were a grain of sand, you would need about 12,500 dump trucks full of sand to hold them all. If every star were a second in time, 1 trillion seconds would be about 32,000 years. If every star were $1, $1 trillion would be enough to give every person on Earth about $125,000. These comparisons help, but they still don't capture the full scale of what we're talking about. Because stars aren't just points of light scattered through space. Each star is a massive ball of plasma, typically similar in size to our Sun or larger. Many stars have planets orbiting them. Some of those planets might have life. And all of this exists in a single galaxy, Andromeda, that we can see as a faint smudge in our night sky. The mass of Andromeda is estimated at about 1.5 trillion times the mass of the Sun, similar to or slightly more than the Milky Way's total mass when you include dark matter. This mass includes all the stars, all the gas and dust, all the planets and moons and asteroids, and all the dark matter that holds the galaxy together. The bulk of this mass, probably about 85%, is dark matter. We can't see dark matter, but we know it's there because of how it affects the motion of visible matter. Stars in the outer regions of Andromeda are moving too fast to be held in orbit by the gravity of the visible matter alone. There must be additional mass, invisible mass, providing the extra gravity needed to keep those stars from flying off into space. That's dark matter. At the center of Andromeda, like at the center of most large galaxies, sits a supermassive black hole. Andromeda's central black hole has a mass of about 140 million times the mass of the Sun. 140 million solar masses. For comparison, the supermassive black hole at the center of the Milky Way, Sagittarius A star, has a mass of about 4 million solar masses. So, Andromeda's central black hole is about 35 times more massive than ours. This black hole has an enormous gravitational influence on its surroundings. Stars near the galactic center orbit the black hole at incredible speeds, some reaching a significant fraction of the speed of light. These stars are trapped in tight orbits, whipping around the black hole in periods of just a few years or decades. But even the black hole, as massive as it is, represents only a tiny fraction of the galaxy's total mass. Most of the galaxy's mass is spread out through the dark matter halo, a roughly spherical cloud of dark matter that extends far beyond the visible boundaries of the galaxy. Andromeda's spiral structure is similar to the Milky Way's, but with some differences. Andromeda is classified as an SAB galaxy, meaning it's a spiral galaxy with tightly wound spiral arms and a prominent central bulge. The spiral arms are where most of the star formation happens. Young, hot, blue stars light up these arms, along with regions of glowing gas where new stars are being born. Between the spiral arms, the galaxy is filled with older, cooler, redder stars. These stars have been around for billions of years, and they no longer shine as brightly as their younger counterparts. The central bulge of Andromeda is densely packed with stars. In this region, stars are much closer together than they are in the outer spiral arms. If you were on a planet in the central bulge, your night sky would be filled with thousands of bright stars, far more than we see from Earth. The galactic center would be a brilliant, glowing region dominating the sky, but the central bulge is also a chaotic place. The density of stars means that close encounters between stars are more common. Gravitational interactions can disrupt planetary systems, or even eject planets from their orbits entirely. And the supermassive black hole at the center adds to the chaos, occasionally consuming stars that wander too close. Andromeda also has a disk component, similar to the Milky Way. The disk is the flattened region where the spiral arms reside. It's about 1,000 light-years thick near the Sun's position in the Milky Way, and probably similar in Andromeda. Most of the galaxy's stars and gas are concentrated in the disk. Surrounding the disk is the halo, a roughly spherical region containing older stars, globular clusters, and dark matter. The halo extends far beyond the visible disk, reaching out to hundreds of thousands of light-years from the galactic center. Globular clusters are particularly interesting. These are dense, spherical collections of hundreds of thousands or even millions of stars. Andromeda has about 450 globular clusters orbiting it, more than twice the number orbiting the Milky Way. These clusters formed early in the galaxy's history and have been orbiting the galactic center ever since. Each globular cluster is like a mini-galaxy in its own right, a self-contained system of stars bound together by gravity. The stars in globular clusters are among the oldest in the universe, often more than 10 billion years old. Studying these ancient stars helps astronomers understand what the early universe was like and how galaxies formed and evolved over time. Andromeda also has satellite galaxies, smaller galaxies that orbit around it. We've identified at least 14 satellite galaxies so far, though there are probably more that we haven't detected yet. The largest of these satellites is Messier 32, a dwarf elliptical galaxy about 6,500 light-years across. M32 contains several billion stars and orbits Andromeda at a distance of about 130,000 light-years from Andromeda's center. Another notable satellite is Messier 110, a dwarf elliptical galaxy about 17,000 light-years across. M110 contains about 15 billion stars and orbits at a similar distance to M32. These satellite galaxies are reminders of Andromeda's violent past. Andromeda didn't grow to its current size peacefully. It grew by consuming other galaxies. Over billions of years, Andromeda has encountered dozens, maybe hundreds, of smaller galaxies. When a small galaxy gets too close to a large one like Andromeda, the large galaxy's gravity tears the smaller galaxy apart. The stars from the smaller galaxy get scattered and eventually absorbed into the larger galaxy. This process is called galactic cannibalism, and it's how large galaxies like Andromeda and the Milky Way grew to their current sizes. We can see evidence of this cannibalism in Andromeda's structure. There are streams of stars in the outer regions of the galaxy, long, thin structures that trace the paths of smaller galaxies that were torn apart. These streams are the remnants of past meals, so to speak, and this process is ongoing. Andromeda is currently in the process of consuming M32 and M110. Over the next few billion years, these satellite galaxies will be completely torn apart and their stars will be absorbed into Andromeda. The Milky Way has a similar history. We've consumed dozens of smaller galaxies over our lifetime. The Sagittarius dwarf elliptical galaxy is currently being torn apart by the Milky Way's gravity as we speak. So Andromeda and the Milky Way are both galactic cannibals, growing larger by eating their smaller neighbors. But here's where things get really interesting. Andromeda and the Milky Way aren't just neighbors. They're on a collision course. The two galaxies are moving toward each other at about 250,000 miles per hour. That sounds fast, and it is by everyday standards. But on cosmic scales, it's actually quite slow. At this speed, the two galaxies won't collide for another 4 to 4.5 billion years. 4 billion years. That's about as long as Earth has existed so far. It's an almost incomprehensible amount of time. But it's going to happen. The collision is inevitable. The mutual gravity between Andromeda and the Milky Way is pulling them together, and there's nothing that can stop it. Now, when I say collision, you might imagine two solid objects smashing into each other, like cars in a crash. But galaxies aren't solid. They're mostly empty space. The stars in a galaxy are separated by vast distances, light years apart. So when two galaxies collide, the stars don't actually hit each other. Instead, they pass by each other, like two swarms of bees flying through each other. The probability of any two stars actually colliding during a galaxy merger is incredibly small. Space is just too big, and stars are too small. But even though the stars don't collide, their gravitational influence on each other is enormous. Every star pulls on every other star. And when you have hundreds of billions of stars all pulling in different directions, the result is chaos. The neat spiral structures of both galaxies will be scrambled. Stars will be flung into new orbits. Some stars will be ejected from the galaxies entirely, thrown out into intergalactic space. And the gas and dust between the stars, which is much more spread out and easier to disturb, will be compressed and heated. This compression will trigger massive bursts of new star formation. The collision will create thousands of new bright, hot, blue stars lighting up both galaxies. Over time, probably about 2 billion years after the initial collision, the two galaxies will merge completely. The result will be a single large elliptical galaxy containing about 1.5 trillion stars. Astronomers have already given this future galaxy a name, Milky-Way, a combination of Milky Way and Andromeda. Milky-Way will be one of the largest galaxies in our local cosmic neighborhood, but still nothing special on universal scales. There are many elliptical galaxies in the universe, just as large or larger, but for us, for anyone living in the Milky Way or Andromeda at that time, it will be a dramatic transformation. The night sky will change completely. The spiral structure we're used to will be gone, replaced by a more chaotic, three-dimensional distribution of stars. And the central region of Milky-Way will be incredibly dense, filled with stars packed much more tightly than they are today. What will happen to Earth during this collision? That's a complicated question. First, it's important to note that Earth will probably be uninhabitable by the time the collision occurs. Not because of the galaxy collision itself, but because of changes to the Sun. The Sun is gradually getting hotter as it ages. In about 1 billion years, the Sun will be hot enough that Earth's oceans will boil away. The planet will become a barren, lifeless rock. In about 5 billion years, the Sun will expand into a red giant, possibly engulfing Earth entirely. So by the time Andromeda and the Milky Way collide, Earth will likely be long gone. But let's assume, for the sake of argument, that Earth somehow survives until the collision. What would happen? The most likely outcome is that nothing dramatic would happen to Earth itself. As I mentioned, the probability of any two stars actually colliding is incredibly small. The nearest stars from Andromeda would still be many light years away. There would be no immediate danger of a collision with another star, no radiation surge, no gravitational disruption of Earth's orbit. But the Sun's orbit around the galactic center would change. The Sun's current orbit is relatively circular and stable. We orbit the galactic center once every 225 million years or so. But during the galaxy collision, this orbit would become more chaotic. The Sun might be pulled toward Andromeda, or it might be flung outward, away from both galactic centers. Or it might simply have its orbit scrambled, sent into a new path that's more elliptical or more tilted. There's even a chance, though a small one, that the Sun could be ejected from the galaxy entirely during the collision. If that happened, we'd become an intergalactic star system, drifting through the void between galaxies. The night sky would go almost completely dark, with no Milky Way band visible overhead, just the distant glow of a few nearby galaxies. But again, these are all hypothetical scenarios. Earth will almost certainly be uninhabitable long before the collision occurs. Humanity, if it still exists at that point, will have moved on to other star systems, other planets, other homes. Let's talk about Andromeda's motion in more detail, because there's something fascinating happening here. Andromeda is approaching us at about 250,000 miles per hour. But that's not because Andromeda is moving through space at that speed. It's because space itself is expanding. The universe has been expanding since the Big Bang about 13.8 billion years ago. Every galaxy is moving away from every other galaxy because the space between them is literally getting bigger. Think of it like raisins in a rising loaf of bread. As the bread expands, the raisins move apart from each other, not because they're moving through the bread, but because the bread itself is expanding. The same thing happens with galaxies. As space expands, galaxies move apart. But, and this is crucial, this expansion only happens on very large scales. On smaller scales, gravity can overcome the expansion. Andromeda and the Milky Way are close enough that their mutual gravitational attraction is stronger than the expansion of space between them. So even though the universe is expanding, even though most galaxies are moving away from us, Andromeda is moving toward us. Gravity is pulling us together. This is true for the entire local group, the collection of about 50 galaxies that includes the Milky Way, Andromeda, Triangulum, and dozens of smaller dwarf galaxies. All of these galaxies are gravitationally bound to each other. They're not being carried apart by the expansion of space. They're moving around each other, orbiting their common center of mass. But on larger scales, beyond the local group, expansion dominates. The Virgo cluster, the nearest large galaxy cluster to us, is about 54 million light-years away and moving away from us as space expands. The Coma cluster, about 320 million light-years away, is moving away even faster, and galaxies billions of light-years away are receding at speeds approaching the speed of light. So the universe is expanding, but locally, within our cosmic neighborhood, gravity keeps things together. Andromeda's approach toward us is proof of that. Now let's compare Andromeda to some other galaxies to get a sense of where it sits in the cosmic hierarchy. The Triangulum galaxy, also called M33, is the third largest member of the local group after Andromeda and the Milky Way. Triangulum contains about 40 billion stars and is about 60,000 light-years across. That's less than half the size of the Milky Way and only about a quarter the size of Andromeda. Triangulum is a nice-sized galaxy by universal standards, but compared to Andromeda, it's small. The Large Magellanic Cloud, a satellite galaxy of the Milky Way, contains about 10 billion stars. The Small Magellanic Cloud has a few billion stars. These are dwarf galaxies, much smaller than either the Milky Way or Andromeda. But let's look beyond our local neighborhood. Messier 87, a giant elliptical galaxy in the Virgo cluster, contains about 1 trillion stars, similar to Andromeda. But M87 is more massive, overall when you include its dark matter halo. And M87's supermassive black hole is absolutely enormous, with a mass of about 6.5 billion solar masses. That's more than 45 times the mass of Andromeda's central black hole. IC 1010-1 is one of the largest galaxies ever discovered. It's about 6 million light-years across. 6 million light-years. That's about 27 times the diameter of Andromeda. IC 1010-1 contains about 100 trillion stars. 100 trillion. That's 100 times more stars than Andromeda has. This single galaxy contains more stars than many entire galaxy clusters, but IC 1010-1 is exceptional. It's one of the largest galaxies we've ever found. Galaxies like IC 1010-1 are incredibly rare. For every galaxy like IC 1010-1, there are thousands of galaxies smaller than Andromeda. So Andromeda is a large galaxy, but it's not extraordinarily large. It's big, but not uniquely so. There are bigger galaxies out there, but they're rare. Most galaxies in the universe are much smaller than Andromeda. The most common galaxies are dwarf galaxies, containing anywhere from a few million to a few billion stars. They're typically just a few thousand light-years across, and they're everywhere. Every large galaxy like Andromeda is surrounded by dozens or hundreds of these dwarf satellites. So in the grand cosmic hierarchy, Andromeda is in the top tier of galaxy sizes. It's one of the big ones. But it's not an outlier. It's large, but not absurdly so. Let's talk about what Andromeda looks like from Earth in more detail. On a clear, dark night, away from city lights, Andromeda appears as a faint, fuzzy oval. It's located in the constellation Andromeda, about 2.5 degrees south of the star New Andromedae. To the naked eye, it looks like a small cloud or smudge. You might mistake it for a star cluster or a nebula if you didn't know what you were looking at. But through binoculars or a small telescope, more detail becomes visible. You can see the bright central bulge surrounded by a fainter, more diffuse outer region. With a larger telescope, you can start to see the spiral structure, the dark dust lanes threading through the arms, the bright regions where young stars are forming. And with long exposure photography, even more detail emerges. Modern telescopes and cameras can capture incredible images of Andromeda, showing its full spiral structure in exquisite detail. These images reveal the galaxy's true size and beauty. But here's something most people don't realize. When you look at Andromeda with your naked eye, you're only seeing the brightest central region. The full extent of the galaxy, including its faint outer regions, actually covers an area in the sky about 6 times wider than the full moon. 6 times wider than the full moon. If the entire galaxy were bright enough to see with the naked eye, it would dominate a huge portion of the sky. But most of the galaxy is too faint to see without long exposure photography. So what we see is just the tip of the iceberg, the brightest core of a much larger structure. This brings up an interesting point. When we talk about the size of Andromeda, we need to be clear about what we mean. Are we talking about the visible disk, the region where most of the stars are? Or are we including the dark matter halo, which extends much farther? The visible disk of Andromeda is about 220,000 light-years in diameter. That's the region where you can actually see stars if you have a powerful enough telescope. But the dark matter halo extends much farther, possibly out to 1,000,000 light-years or more. At this scale, the boundary between Andromeda and intergalactic space becomes fuzzy. There's no clear edge. The density of matter just gradually decreases until you can't really say where the galaxy ends and space begins. This is true for all galaxies. They don't have sharp boundaries like a table or a wall. They fade out gradually. So when we say Andromeda is 220,000 light-years across, we're really talking about the size of the visible disk, the region where the star density is high enough to be easily detectable. The true extent of the galaxy, including all its dark matter, is much larger. Let's talk about star formation in Andromeda. Star formation is the process by which new stars are born from clouds of gas and dust. In Andromeda, like in the Milky Way, star formation happens primarily in the spiral arms. The spiral arms are regions where the density of gas and dust is higher than average. As the galaxy rotates, gas clouds moving through the spiral arms get compressed. This compression triggers gravitational collapse, and new stars begin to form. The rate of star formation in Andromeda is estimated at about 1 solar mass per year. That means every year, enough gas collapses to form the equivalent of 1 star, the mass of the Sun. For comparison, the Milky Way forms about 1 to 2 solar masses worth of new stars every year, so Andromeda and the Milky Way have similar star formation rates. Both are relatively quiet galaxies in this respect. Some galaxies, particularly those undergoing mergers or other violent interactions, can have star formation rates hundreds or thousands of times higher. These starburst galaxies are forming new stars at an incredible pace, consuming their available gas in just a few 100 million years. But Andromeda is not a starburst galaxy. It's forming stars at a steady, sustainable rate. This has been going on for billions of years and will continue for billions more, at least until the collision with the Milky Way changes everything. One interesting feature of Andromeda is its double nucleus. For years, astronomers thought Andromeda had 2 nuclei, 2 bright central cores close together. It turns out this isn't quite right. What looks like 2 nuclei is actually the true nucleus, where the supermassive black hole resides, and a nearby concentration of old stars. The true nucleus is slightly off-center, displaced from the geometric center of the galaxy by a few light-years. This displacement might be evidence of a past merger with another galaxy. When 2 galaxies merge, their central black holes eventually merge too. But the process can disrupt the central region of the combined galaxy, displacing the nucleus from where you'd expect it to be. Alternatively, the displacement might be caused by interactions with the galaxy's bar structure or other dynamical effects. Astronomers are still working to understand exactly what's going on in Andromeda's core. Andromeda also has a prominent dust ring in its outer regions. This ring is about 75,000 light-years from the galactic center and contains a lot of gas and dust. It's a region where star formation is particularly active. The ring might have formed from a collision with a smaller galaxy about 210 million years ago. The collision would have disturbed the gas in Andromeda's disk, causing it to settle into a ring structure. Or the ring might be a natural feature of the galaxy's spiral structure, a region where gas density is particularly high. Again, astronomers are still studying this feature to understand its origin. Let's talk about the rotation of Andromeda. Like all spiral galaxies, Andromeda rotates. Stars in the disk orbit around the galactic center, following roughly circular paths. The rotation isn't uniform, though. Stars closer to the center orbit faster than stars farther out. Near the center, orbital speeds can reach several hundred miles per second. In the outer regions, speeds are slower, around 60 to 125 miles per second. But here's something interesting. The rotation curve of Andromeda, a plot of orbital speed versus distance from the center, doesn't behave the way you'd expect based on the visible matter alone. According to Newtonian gravity, if you move farther from the center of the galaxy, where there's less visible matter inside your orbit, your orbital speed should decrease. This is how planets in our solar system behave. Mercury, the innermost planet, orbits the Sun at about 107,000 miles per hour. Earth orbits at about 67,000 miles per hour. Neptune, the outermost planet, orbits at only about 12,000 miles per hour. The farther you are from the Sun, the slower you orbit. But in galaxies, this isn't what we observe. Stars in the outer regions of galaxies are moving faster than they should be based on the visible matter. This is one of the key pieces of evidence for dark matter. There must be additional mass, invisible mass, providing the extra gravity needed to keep those outer stars moving so fast. In Andromeda, The rotation curve stays roughly flat out to large distances. Stars in the outer disk are moving at nearly the same speed as stars closer to the center. This tells us that the dark matter halo extends far beyond the visible disk, providing gravitational influence throughout the galaxy. Without dark matter, galaxies like Andromeda couldn't exist. They would fly apart, unable to hold themselves together with just the gravity from visible matter. Dark matter is the glue that holds galaxies together. Let's talk about Andromeda's history. Andromeda formed about 10 billion years ago, roughly 3 to 4 billion years after the Big Bang. It formed from the collapse of a large cloud of gas in the early universe. As the gas collapsed under its own gravity, it began to rotate. The rotation caused the gas to flatten into a disk. Within this disk, stars began to form. Over billions of years, the galaxy grew larger through mergers with other galaxies. Studies of Andromeda's stellar populations suggest it's absorbed several smaller galaxies over its lifetime. You can see evidence of this in streams and shells of stars in the outer regions of the galaxy. These are the remnants of dwarf galaxies that got too close and were torn apart by Andromeda's gravity. About 2 to 4 billion years ago, Andromeda underwent a major merger with another galaxy. This merger significantly increased Andromeda's size and mass. It also disrupted the galaxy's structure, scrambling the orbits of stars and triggering bursts of star formation. The effects of this merger are still visible today in the distribution of stars and gas throughout the galaxy. Since then, Andromeda has been relatively quiet. It's consumed a few smaller galaxies, but there haven't been any major mergers in the recent past. The galaxy has had time to settle into a more stable configuration, developing the spiral structure we see today. But this peaceful period is coming to an end. The upcoming collision with the Milky Way will be the most dramatic event in Andromeda's history since its formation. Let's talk about what it would be like to live in Andromeda. Imagine you're on a planet in one of Andromeda's spiral arms, similar to Earth's position in the Milky Way. Your night sky would look different from ours, but not dramatically so. You'd see a band of light crossing the sky, the combined glow of billions of stars in the galactic disk. This would be Andromeda's version of the Milky Way band we see from Earth. You'd see thousands of individual stars, the brightest ones in your local neighborhood, and you'd see nebulae, glowing clouds of gas where new stars are forming. If you had a telescope, you could observe other galaxies. The Milky Way would be visible as a faint smudge, similar to how we see Andromeda from Earth. You could observe the Triangulum Galaxy, the large and small Magellanic Clouds, and dozens of dwarf galaxies scattered throughout the local group. And if you lived in Andromeda a few billion years from now, you'd see the Milky Way getting larger in the sky year by year, approaching for the inevitable collision. One question people often ask is whether there could be life in Andromeda. The answer is almost certainly yes. With 1 trillion stars, many of which likely have planets, the probability that at least some of those planets harbor life is extremely high. We don't have direct evidence of life in Andromeda, of course. It's too far away to detect individual planets, let alone signs of life on those planets. But based on what we know about life on Earth and the prevalence of planets throughout the universe, it would be shocking if Andromeda didn't have life somewhere within it. Whether that life is intelligent, technological, capable of building civilizations, that's a different question. But simple life, microbial life, life clinging to existence in whatever environments are available, that almost certainly exists in Andromeda. And if there are intelligent civilizations in Andromeda, they would face the same questions we face. Where did we come from? What is the universe? Are we alone? They would look up at their night sky and see the same cosmic structures we see. The same galaxies, the same clusters, the same large-scale patterns. They would discover the same laws of physics, the same fundamental forces, the same mathematical relationships that govern the universe, because the universe is the same everywhere. The laws of physics are universal, and intelligent beings, no matter where they are, no matter how different their biology or their culture, would discover the same truths about reality. Andromeda's spiral arms contain some of the most spectacular star-forming regions in the local group. These regions are where molecular clouds, giant collections of cold gas and dust, collapse under their own gravity to form new stars. The process is triggered when the clouds are compressed, either by the passage through a spiral arm density wave or by shock waves from nearby supernova explosions. Once compression begins, the densest parts of the cloud collapse first. As the cloud collapses, it fragments into smaller pieces. Each fragment continues collapsing until the core becomes dense enough and hot enough to ignite nuclear fusion. At that point, a star is born. The newly formed star begins emitting light and stellar wind, clearing away the surrounding gas and dust. If you could observe one of these star-forming regions up close, you'd see something incredible. Young stars, only a few million years old, blazing brilliant blue-white. These are massive stars, much larger than our sun, burning through their fuel at an incredible rate. They'll only live for a few million years before exploding as supernovae. Around these young stars, you'd see the remnants of the molecular cloud they formed from, glowing nebulae lit up by the intense ultraviolet radiation from the hot stars. And embedded within these nebulae, you'd see even younger stars still forming, protostars that haven't yet begun true nuclear fusion, surrounded by thick cocoons of dust. These star-forming regions are often clustered together in complexes spanning hundreds of light-years. One such complex in Andromeda contains dozens of individual star-forming regions, each one producing hundreds or thousands of new stars. The total rate of star formation in this single complex is several solar masses per year, comparable to the star formation rate of some entire small galaxies. When you observe Andromeda in ultraviolet light, these star-forming regions light up like beacons. The ultraviolet emission comes from the hottest, youngest stars, those massive blue giants that formed within the last few million years. In visible light, these regions appear as bright blue patches scattered throughout the spiral arms. The blue color comes from those same young, hot stars. Hot stars emit more blue light than cool stars, so regions with lots of young stars appear blue. In contrast, regions with mostly older stars appear more yellow or red. The central bulge of Andromeda appears yellow-orange because it's dominated by older, cooler stars. These stars formed billions of years ago when the galaxy was young, and they're still shining today, though not as brightly as they once did. In infrared light, you can see the dust. Dust blocks visible and ultraviolet light, but it emits infrared radiation. Observations in infrared reveal intricate structures of dust lanes threading through Andromeda's spiral arms. These dust lanes are where star formation will occur in the future. The dust is part of the molecular clouds I mentioned earlier, the raw material from which new stars form. Radio observations reveal even more. At radio wavelengths, you can detect the emission from cold hydrogen gas, the most abundant element in the universe. This gas fills the space between stars and provides much of the raw material for star formation. Mapping the distribution of hydrogen gas in Andromeda reveals the galaxy's rotation, shows where gas is being compressed in the spiral arms, and highlights regions where gas has been blown away by supernova explosions or stellar winds from massive stars. X-ray observations show the most energetic phenomena in the galaxy. X-rays come from extremely hot gas heated to millions of degrees. This can happen in several ways. Supernova remnants, the expanding shells of material ejected when massive stars explode, emit X-rays as the material plows into surrounding gas. Binary star systems, where one star is pulling material off its companion, can create X-ray emission as the material spirals inward and heats up. And the region around the central supermassive black hole can emit X-rays when material falls toward the black hole and heats to incredible temperatures. By observing Andromeda at multiple wavelengths, astronomers build up a comprehensive picture of the galaxy's structure and activity. Each wavelength reveals something different, and together they show us a galaxy that is far more complex and dynamic than it appears to the naked eye. Let's talk more about the central supermassive black hole. As I mentioned, Andromeda's central black hole has a mass of about 140 million solar masses. That makes it one of the more massive supermassive black holes in our cosmic neighborhood, though far from the most massive in the universe. The black hole M87, for example, has a mass of about 6.5 billion solar masses, roughly 45 times more massive than Andromeda's. And there are black holes even more massive than that, approaching tens of billions of solar masses. But 140 million solar masses is still enormous by any reasonable standard. To put this in perspective, if you replace the Sun with Andromeda's central black hole, the black hole's event horizon, the boundary beyond which nothing can escape, would extend out to about 415 million miles. That's roughly the distance from the Sun to the asteroid belt. The entire inner solar system, including Earth, Mars, and everything in between, would fit inside the black hole's event horizon. Of course, if you were anywhere near a black hole this massive, you'd be in serious trouble. The gravitational pull would be immense. Tidal forces, the difference in gravitational pull between your head and your feet, would become significant at distances of hundreds of millions of miles from the black hole. Get too close, and you'd be stretched and compressed by tidal forces in a process astronomers call spaghettification. Your body would be stretched into a long, thin shape like a piece of spaghetti before being torn apart. But for stars orbiting at safe distances, hundreds or thousands of light years from the black hole, the gravitational influence is more subtle. The black hole affects the orbits of nearby stars, causing them to move in elliptical paths around the galactic center. Stars very close to the black hole, within a few light years, orbit at incredible speeds. Some of these stars complete an orbit in just a few years, moving at a significant fraction of the speed of light at their closest approach. Studying the orbits of these stars is one of the ways astronomers measure the mass of the central black hole. By tracking how fast stars are moving and the shape of their orbits, you can calculate how much mass is pulling on them. And the only way to explain the observed motions is if there's an enormous concentration of mass at the galactic center, something with the mass of 140 million suns, but confined to a region smaller than our solar system. That's a black hole. The only object that can pack that much mass into such a small space. Interestingly, Andromeda's central black hole appears to be relatively quiet right now. It's not actively feeding on large amounts of material, so it's not producing the bright emission that active galactic nuclei can produce. An active galactic nucleus, or AGN, occurs when a supermassive black hole is actively consuming gas and dust. The material spirals inward, forming an accretion disk around the black hole. Friction in the disk heats the material to millions of degrees, causing it to emit intense radiation across the electromagnetic spectrum. In the most extreme cases, the black hole can produce jets of matter and energy that shoot out from the poles, extending for thousands or even millions of light years into space. These jets can be so bright that they outshine the entire galaxy. But Andromeda's central black hole is not doing this right now. It's relatively dormant, consuming only small amounts of material, producing only modest emission. This might not always have been the case. There's evidence that many supermassive black holes go through active periods when they consume large amounts of material, interspersed with quiet periods like the one Andromeda is in now. During an active period, the black hole's environment would be dramatically different. The intense radiation from the accretion disk would ionize gas throughout the central region of the galaxy. The jets, if they formed, would plow through the surrounding gas, creating shock waves and heating the gas to millions of degrees. Star formation in the central region might be suppressed by the intense radiation and by the jets blowing gas away. But right now, Andromeda's central black hole is quiet. And that's probably a good thing for any hypothetical civilizations living in the central regions of the galaxy. An active AGN would make life much more difficult, bathing the surrounding region in intense radiation. Let's talk more about Andromeda's satellite galaxies. I mentioned Messier 32 and Messier 110 earlier, but there are many more. So far, we've identified at least 14 satellite galaxies orbiting Andromeda, and there are probably more that we haven't detected yet. These satellites range in size from relatively large dwarf ellipticals like M32, which contain several billion stars, down to tiny dwarf spheroidals with only a few 100,000 stars. The smallest satellites are incredibly faint and difficult to detect. They're only visible because they're relatively close to us, cosmically speaking. If they were at the distance of the Virgo cluster or beyond, we'd never be able to see them with current telescopes. Studying these satellite galaxies is important for understanding how large galaxies like Andromeda formed and evolved. The prevailing theory of galaxy formation, called hierarchical assembly, suggests that large galaxies formed through the merger and accretion of many smaller galaxies. In the early universe, small galaxies formed first. Over time, these small galaxies collided and merged, forming progressively larger galaxies. This process continues today, though at a slower rate than in the early universe when galaxies were more closely packed together. The satellite galaxies orbiting Andromeda are remnants of this process. They're the survivors, the small galaxies that happen to end up in orbit around Andromeda rather than colliding with it directly. But their survival is temporary. Over time, tidal forces from Andromeda's gravity will tear them apart. Some will be disrupted completely, their stars scattered throughout Andromeda's halo. Others might survive longer, maintaining their coherence for billions of years. But eventually, all of them will be consumed. We can see this process happening in real time with some of Andromeda's satellites. M32, for example, shows signs of tidal distortion. Its outer regions are being stripped away by Andromeda's gravity. In a few billion years, M32 might be completely absorbed, its stars becoming part of Andromeda's halo. The same thing is happening with some of the Milky Way's satellites. The Sagittarius dwarf elliptical galaxy is currently being torn apart as it orbits the Milky Way. Streams of stars from this galaxy can be traced, wrapping around the entire Milky Way, evidence of past passages when the galaxy swung close and had stars pulled away. This is how large galaxies grow. Not just through major mergers with other large galaxies, though those happen too, but through the gradual consumption of smaller satellites over billions of years. It's a process called galactic cannibalism, and it's happening constantly throughout the universe. Every large galaxy is slowly eating its smaller neighbors. Now let's talk about what would happen during the collision with the Milky Way in more detail. 4 billion years from now, give or take a few 100 million years, the Milky Way and Andromeda will begin their first passage. By this time, Andromeda will dominate the night sky, stretching across a huge portion of the heavens. The two galaxies will be close enough that their outer edges are beginning to overlap. Tidal forces will have already started to distort both galaxies, creating long streamers of stars extending toward and away from each other. These tidal tails are a characteristic feature of galaxy mergers. They form because the side of each galaxy closest to the other feels a stronger gravitational pull than the side farther away. This differential force stretches the galaxy, pulling it into an elongated shape. As the galaxies continue to approach, the tidal tails grow longer and more prominent, eventually extending for hundreds of thousands of light years. During the first passage, the two galaxies will swing past each other, their stars intermixed, but not yet merged. The close encounter will further scramble the orbits of stars in both galaxies. Stars that were following nice, circular orbits around their respective galactic centers will be flung into more chaotic, elliptical orbits. Some stars will be ejected from the galaxies entirely, thrown out into intergalactic space, with enough velocity to escape the combined gravitational pull of both galaxies. These stars will become intergalactic wanderers, drifting through the void between galaxies with no home to return to. The probability of any individual star being ejected is small, but with hundreds of billions of stars involved, millions or even billions could end up in intergalactic space. Gas clouds will be affected even more dramatically than stars. Unlike stars, which are separated by vast distances and rarely interact directly, gas clouds can collide and merge. When gas clouds from the two galaxies collide, they compress and heat up. This compression triggers massive bursts of new star formation. The collision will create what astronomers call a starburst, a period of intense star formation far exceeding the normal rate. During a starburst, a galaxy can form stars hundreds or even thousands of times faster than usual. In Andromeda and the Milky Way's merger, the starburst won't be quite that extreme, but star formation will definitely increase dramatically. The new stars formed during the starburst will be predominantly massive, hot, blue stars. These stars burn through their fuel quickly, living for only a few million years before exploding as supernovae. So the night sky during the merger will be spectacular. Bright blue regions of new star formation will light up the disrupted spiral structures. Supernovae will flash across the sky, some bright enough to be visible during the day. The combined glow from billions of stars in both galaxies will create a magnificent, chaotic light show. After the first passage, the two galaxies will separate again. They'll swing apart, pulled by their own momentum, but they won't separate completely. Gravity will slow them down, bring them to a halt, and then pull them back together for a second passage. This second passage, occurring a few 100 million years after the first, will be even more dramatic. The galaxies will have lost some energy during the first passage, so they'll be moving slower when they meet again. This means they'll spend more time close together, allowing tidal forces more time to work. The spiral structures will be even more disrupted. The tidal tails will be longer and more complex, and the starburst will intensify as more gas clouds collide and compress. There might be a third passage, possibly even a fourth, each one further mixing the two galaxies. With each passage, the galaxies lose energy through several mechanisms. Some energy goes into ejecting stars into intergalactic space. Some goes into heating gas through collisions and compression. And some is radiated away as gravitational waves, ripples in space-time, produced by the massive accelerating objects. Eventually, after 1 billion or 2 billion years of this back and forth, the two galaxies will merge completely. The final product will be a single large elliptical galaxy containing about 1.5 trillion stars. This galaxy, which astronomers have nicknamed Milky-Way, will no longer have the spiral structure of its parent galaxies. Instead, it will be roughly spherical or elliptical, with stars distributed in a three-dimensional, chaotic arrangement rather than concentrated in a flat disk. The central supermassive black holes from both galaxies will eventually merge as well. During the early stages of the merger, each black hole will sink toward the center of the combined system. As they sink, They'll eject stars through gravitational slingshot interactions, where a star passes close to one of the black holes and gets flung out at high speed. Eventually, the two black holes will meet and begin orbiting each other. This binary black hole system will emit gravitational waves, slowly losing energy until the black holes finally merge. The merger will take millions of years, but when it happens, it will be the most powerful event in the history of both galaxies. The two black holes, one with a mass of about 4 million solar masses from the Milky Way, and one with a mass of about 140 million solar masses from Andromeda, will combine to form a single black hole with a mass of about 144 million solar masses. Some mass, roughly equivalent to a few million solar masses, will be converted directly into gravitational waves during the final moments of the merger. These gravitational waves will propagate outward at the speed of light, carrying away the energy and angular momentum of the merger. If there were any gravitational wave detectors in the local group at that time, they would record an incredibly powerful signal, far stronger than any gravitational wave signal detected by current instruments on Earth. The merged black hole might receive a kick, a recoil effect from the asymmetric emission of gravitational waves. This kick could send the black hole moving through the galaxy at hundreds or thousands of miles per second. Eventually, it would slow down and settle at the center of Milky-Way, but for a while, it might wander. After the merger is complete, after Milky-Way has settled into its final form, star formation will gradually decline. Most of the available gas will have been used up during the starburst phase of the merger. Some gas will have been heated to such high temperatures that it escapes the galaxy entirely, blown away by supernova explosions and stellar winds. What remains will be a galaxy dominated by older, cooler stars, slowly aging as its stellar population evolves. Milky-Way will join the ranks of the giant elliptical galaxies scattered throughout the universe, a monument to the merger of two once great spiral galaxies. Let's talk about observing Andromeda throughout history. Andromeda has been known since ancient times. The Persian astronomer Abd al-Rahman al-Sufi described it in the year 964, calling it a small cloud. Chinese astronomers recorded observations of Andromeda as early as 905. But for most of history, people didn't know what Andromeda actually was. They thought it was just a nebula, a cloud of gas within our own galaxy. It wasn't until the early 20th century that astronomer Edwin Hubble proved Andromeda was a separate galaxy. Hubble used the 100-inch telescope at Mount Wilson Observatory to observe individual stars within Andromeda. He identified a type of star called Cepheid variables, which pulsate with regular periods. The period of pulsation is related to the star's intrinsic brightness. By measuring the period, you can determine how bright the star really is. Then, by comparing the star's true brightness to how bright it appears from Earth, you can calculate the distance. Hubble's measurements showed that Andromeda was about 900,000 light-years away. We now know the actual distance is about 2.5 million light-years, so Hubble's initial estimate was too small by a factor of about 3. But it was still clearly far beyond the Milky Way's boundaries. This discovery fundamentally changed our understanding of the universe. Suddenly, the cosmos was much larger than anyone had imagined. Our galaxy wasn't the entire universe. It was just one island in an ocean of galaxies. And Andromeda was another island, just as large, just as complex, filled with billions of stars and untold numbers of worlds. Since Hubble's discovery, our knowledge of Andromeda has grown enormously. Let's talk about some of the specific structures within Andromeda that make it so fascinating. Andromeda contains approximately 450 globular clusters. These are dense, spherical collections of stars that orbit the galaxy like satellites. Each globular cluster contains hundreds of thousands to millions of stars, packed into a region typically about 100 to 200 light-years across. The stars in globular clusters are among the oldest in the galaxy, often more than 10 billion years old. They formed in the early universe, not long after the first generation of stars. Because they're so old, globular clusters contain almost no elements heavier than hydrogen and helium. The reason is that heavier elements, what astronomers call metals, are produced inside stars and dispersed into space when stars die. The first generation of stars formed from the pristine hydrogen and helium created in the Big Bang. When those stars exploded as supernovae, they enriched the surrounding gas with heavier elements. The next generation of stars formed from this enriched gas, so they contained more metals. This process has continued for billions of years, with each successive generation of stars containing more metals than the last. Globular clusters formed very early, so their stars have very low metallicity. This makes them valuable laboratories for studying the early universe and the first generations of star formation. One of Andromeda's most prominent globular clusters is called Male 2, though it's also designated G1. This cluster is one of the most massive globular clusters in the local group. It contains several million stars and has a total mass of about 10 million solar masses. That's roughly twice the mass of Omega Centauri, the most massive globular cluster in the Milky Way. G1 orbits Andromeda at a distance of about 130,000 light-years from the galactic center. It's bright enough that it can be observed even from relatively small telescopes here on Earth. The cluster appears as a faint, fuzzy point of light, but through larger telescopes, you can resolve individual stars within it. Studying globular clusters like G1 helps astronomers understand Andromeda's formation history. The distribution of globular clusters, their ages, their metallicities, all provide clues about how and when the galaxy formed. Some globular clusters likely formed with Andromeda itself, condensing from the same gas cloud that formed the galaxy. Others might have been captured from smaller galaxies that Andromeda consumed over its history. By studying the properties of different globular clusters, astronomers can piece together a history of Andromeda's evolution. Andromeda also contains a prominent stellar stream called the Giant Southern Stream. This is a long, thin structure of stars extending for hundreds of thousands of light-years through Andromeda's halo. The stream is believed to be the remnant of a dwarf galaxy that Andromeda consumed sometime in the past few billion years. When a small galaxy gets too close to a large one like Andromeda, tidal forces tear it apart. The stars from the disrupted galaxy get stretched out into a long stream that follows the orbit of the original galaxy. Over time, this stream wraps around the larger galaxy, eventually spreading out and becoming part of the halo. The Giant Southern Stream is a beautiful example of this process caught in action. We're seeing the remnants of a galaxy that no longer exists, its stars now scattered throughout Andromeda's outer regions. Similar streams exist in the Milky Way. The Sagittarius Stream, for example, wraps completely around our galaxy, tracing the orbit of the Sagittarius dwarf elliptical galaxy as it's slowly being torn apart. These streams are important because they're direct evidence of the hierarchical assembly process I mentioned earlier. They show us that large galaxies, like Andromeda and the Milky Way, grew by consuming smaller galaxies, and they're still growing today through this same process. Let's talk about some of the specific regions within Andromeda's disk. Andromeda has several major star-forming complexes, regions where new stars are being born at an accelerated rate. One of the largest is called NGC 210-6. This is an emission nebula, a cloud of gas ionized by radiation from nearby hot stars. It's located about 22,000 light-years from Andromeda's center, out in one of the spiral arms. NGC 206 is enormous, about 4,000 light-years across. That makes it one of the largest emission nebulae in the local group, significantly larger than the Orion Nebula in the Milky Way, which is only about 24 light-years across. The nebula is home to hundreds of young, hot stars, many of them dozens of times more massive than the Sun. These stars are blasting the surrounding gas with intense ultraviolet radiation, causing it to glow brightly. The nebula appears red in images because of emission from hydrogen gas, which produces a characteristic red color when ionized. Star formation is still ongoing within NGC 206. Embedded within the visible nebula are dense clouds of dust and gas, where new stars are forming right now. These regions are opaque to visible light, but they can be studied using infrared or radio observations that penetrate the dust. Another interesting feature of Andromeda is its ring-like structure in the outer disk. At a distance of about 75,000 light-years from the center, there's a ring of gas and dust where star formation is particularly active. This ring contains several large star-forming regions and a significant fraction of the galaxy's cold gas. The origin of this ring is somewhat mysterious. One theory is that it formed from a collision with another galaxy, perhaps M32, about 210 million years ago. The collision would have sent a ripple through Andromeda's disk, compressing gas and triggering star formation in a ring-like pattern. Alternatively, the ring might be a natural feature of the galaxy's spiral structure, a region where the density of gas is particularly high due to the gravitational dynamics of the disk. Astronomers are still studying this feature to understand its origin and evolution. Let's compare Andromeda to some other galaxies beyond those I've already mentioned. The Sombrero Galaxy, Messier 104, is a beautiful spiral galaxy about 31 million light-years away. It's notable for its extremely prominent central bulge and a thick dust lane that circles the galaxy's edge-on disk. The Sombrero Galaxy is about 50,000 light-years across, roughly half the diameter of Andromeda. But it has an enormous central black hole, about 1 billion solar masses, which is more than 7 times more massive than Andromeda's black hole, despite the galaxy being smaller. This tells us that there's not always a direct correlation between galaxy size and black hole mass. Some galaxies have unusually massive black holes relative to their size, and we're still working to understand why. The Whirlpool Galaxy, Messier 51, is another beautiful spiral about 23 million light-years away. It's about 76,000 light-years in diameter, smaller than Andromeda but similar in structure. What makes the Whirlpool Galaxy particularly interesting is that it's currently interacting with a smaller companion galaxy, NGC 5195. The interaction is creating dramatic tidal features and triggering intense star formation in both galaxies. This gives us a preview of what might happen during the early stages of the Milky Way-Andromeda collision. The Whirlpool Galaxy's spiral arms are incredibly well-defined, making it one of the most photogenic galaxies in the sky. NGC 639, sometimes called the Box Galaxy, is a spiral galaxy about 400,000 light-years across. That's nearly twice the diameter of Andromeda. It's one of the largest spiral galaxies known, containing trillions of stars. But despite its size, NGC 639 is relatively faint because its stars are spread out over such a large area. This makes it difficult to observe, and it was only discovered relatively recently in astronomical terms. Malin 1 is even larger, about 650,000 light-years across. It's what's called a giant, low-surface brightness spiral galaxy. It contains a lot of stars and gas, but they're distributed over such an enormous volume that the galaxy appears very faint. Malin 1 wasn't discovered until 1986, despite being relatively nearby in cosmic terms. These giant spirals are rare, though. For every galaxy like NGC 639 or Malin 1, there are thousands of galaxies smaller than Andromeda. The elliptical galaxies represent a different type of structure entirely. As I mentioned earlier, ellipticals form primarily through galaxy mergers. When two spiral galaxies collide, the result is often an elliptical galaxy. The beautiful spiral structure gets disrupted and destroyed during the merger, and what remains is a more chaotic, three-dimensional distribution of stars. Messier 87, which I've mentioned several times, is a giant elliptical galaxy in the Virgo cluster. It's about 120,000 light-years across, similar to Andromeda in diameter. But M87 contains about 1 trillion stars, similar to Andromeda, and it's significantly more massive when you include dark matter. What really sets M87 apart is its supermassive black hole, which has a mass of about 6.5 billion solar masses. This is the black hole that was famously imaged by the Event Horizon telescope in 2019, producing the first ever direct image of a black hole's event horizon. The black hole is actively feeding, consuming gas and dust, and producing enormous jets of matter and energy that extend for thousands of light-years into space. If Andromeda's black hole were as active as M87's, the central regions of our galaxy would be dramatically different. The intense radiation would make the galactic center visible from Earth, even through all the intervening dust, and the jets would be detectable across the electromagnetic spectrum. But Andromeda's black hole is quiet, at least for now. IC 1010-1, which I mentioned earlier, deserves more discussion because it's such an extreme example. This galaxy is about 6 million light-years across, roughly 27 times the diameter of Andromeda. It contains about 100 trillion stars, 100 times more than Andromeda. Its dark matter halo has a mass of about 60 to 100 trillion solar masses. To put this in perspective, if you replaced Andromeda with IC 1010-1, it would stretch from where Andromeda currently is all the way past the Milky Way and beyond. The galaxy would fill a huge portion of the sky, visible even during the day. But IC 1010-1 is not a normal galaxy. It's the result of the merger of multiple large galaxies over billions of years. It sits at the center of the Abell 2029 galaxy cluster, and it's grown so large by consuming other galaxies in the cluster. This process is still ongoing. IC 1010-1 continues to grow, slowly absorbing smaller galaxies that wander too close. Over time, it will become even larger. But galaxies like IC 1010-1 are incredibly rare. They can only form in the centers of large galaxy clusters where there are lots of other galaxies to consume. And they take billions of years to grow to such enormous sizes. Andromeda, by comparison, is a normal, large spiral galaxy. It's big, yes, but it's not extraordinary. There are thousands of galaxies similar to Andromeda throughout the observable universe, and there are millions of galaxies smaller than Andromeda. So, where does Andromeda sit in the cosmic hierarchy? It's in the top tier, certainly. Probably in the top few percent of galaxies by size and mass. But it's not unique. It's one of many large spiral galaxies scattered throughout space. Let's talk about the dark matter in Andromeda, because this is one of the most important and mysterious aspects of the galaxy. As I mentioned earlier, about 85% of the matter in Andromeda is dark matter. We can't see dark matter directly because it doesn't emit, absorb, or reflect light, but we know it's there because of its gravitational effects. The rotation curve of Andromeda, the plot of how fast stars are moving at different distances from the galactic center, doesn't match what you'd expect based on the visible matter alone. Stars in the outer regions are moving too fast. They should be flying off into space, unable to maintain their orbits around the galactic center. But they're not flying off. Something is holding them in. That something is dark matter. The dark matter halo extends far beyond the visible disk of the galaxy, providing the gravitational glue that holds everything together. Computer simulations of galaxy formation consistently show that galaxies cannot form without dark matter. In simulations that only include ordinary matter, gas, stars, dust, the structures that form don't look like real galaxies. They're too small, too diffuse, too unstable. Only when you include dark matter do the simulations produce galaxies that match what we observe. The dark matter provides the gravitational framework, the skeleton upon which the visible galaxy is built. Gas falls into the dark matter halo, collects in the center, and begins to form stars. Without the dark matter halo, the gas would never accumulate in sufficient quantities to form a galaxy. So what is dark matter? We don't know. That's one of the biggest unsolved questions in physics. We know dark matter exists because of its gravitational effects, but we don't know what it's made of. It's not ordinary matter, not atoms made of protons, neutrons, and electrons. We know this because there's not enough ordinary matter in the universe to explain the gravitational effects we observe. The leading candidates for dark matter are exotic particles that were produced in the early universe shortly after the Big Bang. These particles would interact very weakly with ordinary matter, passing through it almost as if it weren't there. The only significant interaction would be gravitational. Physicists have proposed several specific particle candidates. Weakly interacting massive particles, or WIMPs, are one possibility. Axions, much lighter particles originally proposed to solve a problem in particle physics, are another. Sterile neutrinos, hypothetical cousins of the known neutrinos, are a third option. And there are others. Experiments around the world are searching for these particles, trying to detect them directly. So far, no direct detection has been confirmed, though there have been some tantalizing hints that haven't been confirmed by follow-up experiments. The search continues. Understanding dark matter is one of the highest priorities in physics because it's crucial to understanding how the universe works. Dark matter makes up 27% of the total energy density of the universe. Ordinary matter, everything we can see, makes up only about 5%. The remaining 68% is dark energy, an even more mysterious form of energy that's causing the expansion of the universe to accelerate. But that's a topic for another time. For Andromeda, the presence of dark matter is essential to its existence. Without dark matter, there would be no Andromeda Galaxy. The gas that formed the galaxy never would have come together in the first place. And if the dark matter halo somehow disappeared today, Andromeda would quickly fly apart, its stars scattered into intergalactic space. Let's return to the topic of the collision with the Milky Way and explore what will happen to individual star systems during the merger. Imagine you're living on a planet orbiting a star in the Milky Way's disk when the collision begins. At first, you'd notice changes in the night sky. Andromeda, which today appears as a small, faint smudge, would grow larger year by year. Over millions of years, it would expand to fill a larger and larger portion of the sky. By the time the first passage occurs, Andromeda would be huge, stretching across perhaps a third of the visible sky. You'd be able to see its spiral structure with the naked eye, the bright central bulge, the sweeping arms, the dark dust lanes. Individual bright stars in Andromeda would be visible, those that are especially luminous or happen to be relatively nearby by galactic standards. The combined light from Andromeda and the Milky Way would make the night sky brighter than it is today. Instead of seeing a faint band of the Milky Way, you'd see two bright structures crossing the sky, the remains of both galaxies' disks. But despite the spectacular view, your daily life probably wouldn't change much. The sun would still rise and set. The seasons would still change. Your planet would continue orbiting your star just as it always has. The nearest stars from Andromeda would still be many light years away, far too distant to have any direct effect on your solar system. The probability of a close encounter with another star is incredibly small. Space is so vast and stars are so small that even in the thick of a galaxy collision, most stars never come close to each other. Computer simulations of galaxy mergers typically track millions of particles, each representing a clump of stars. Even in these simulations where millions of stars are tracked, direct collisions are rare. In reality, with hundreds of billions of actual stars, the probability of any two stars colliding is vanishingly small. It's been estimated that during the entire Milky Way-Andromeda merger, maybe a few tens of thousands of stars might collide out of the combined trillion-plus stars in both galaxies. That's a tiny fraction, less than 0.001%, so the odds of your star colliding with another star are essentially zero. But that doesn't mean your star system would be completely unaffected. The Sun's orbit around the galactic center would change. Right now, the Sun follows a roughly circular orbit, completing one loop around the Milky Way every 225 million years or so. But during the merger, gravitational interactions with stars from Andromeda and tidal forces from Andromeda's overall mass distribution would perturb this orbit. The Sun might be pulled into a more elliptical orbit, one that takes it closer to the galactic center at some points and farther away at others. Or the orbit might be tilted relative to the galactic plane, sending the Sun up above or below the disk. In more extreme cases, the Sun could be ejected from the galaxy entirely. This would require a close encounter with a particularly massive object, perhaps a cluster of stars or a dense gas cloud. The odds of this happening are small, but not zero. If the Sun were ejected, we'd become an intergalactic star system, drifting through the void between galaxies. The night sky would change dramatically. Instead of seeing the combined glow of the Milky Way and Andromeda, you'd see mostly darkness. The nearest galaxy would be millions of light-years away, appearing as tiny, faint smudges, even through powerful telescopes. You'd be truly alone, drifting through the cosmic void with no galactic home. It's a sobering thought, though again, the probability of this happening to any individual star system is quite small. Most stars will remain bound to the merged galaxy, though their orbits will be scrambled. But let's talk about something else that would happen during the merger that I haven't discussed much yet. The gas between the stars would collide and compress, as I mentioned, triggering starbursts. But some of this gas would be heated to such extreme temperatures that it would escape the galaxy entirely. This process is called galactic superwinds. When massive stars form during the starburst, they live fast and die young, exploding as supernovae after only a few million years. Each supernova explosion releases enormous amounts of energy, heating the surrounding gas to millions of degrees. Hundreds or thousands of supernovae exploding over a relatively short time period, astronomically speaking, create enormous bubbles of hot gas. These bubbles expand, merge with other bubbles, and eventually break through the disk of the galaxy, venting hot gas into the halo and beyond. This process removes gas from the galaxy, reducing the amount of material available for future star formation. It's one of the ways galaxies regulate their own star formation. Too much star formation leads to lots of supernovae, which blow away the remaining gas, shutting down star formation until more gas can accumulate. During the Milky Way-Andromeda merger, this process will be especially intense. The starburst will produce so many supernovae that significant amounts of gas will be ejected from both galaxies. This ejected gas might eventually fall back onto the merged galaxy, or it might escape entirely, lost to the intergalactic medium. The net effect is that Milky-Andromeda, the merged galaxy, will have less gas available for star formation than the two parent galaxies had combined. This is one reason why elliptical galaxies like Milky-Andromeda will tend to have lower star formation rates than spiral galaxies. Much of their gas was either consumed during the merger, starburst, or blown away by supernovae and stellar winds. Let's talk about observing Andromeda with modern technology. Today, We have an incredible array of telescopes and instruments that allow us to study Andromeda in unprecedented detail. The Hubble Space Telescope has produced some of the most spectacular images of Andromeda ever taken. In 2015, astronomers released a panoramic image of Andromeda taken by Hubble. This image contains about 1.5 billion pixels and shows a section of the galaxy about 40,000 light-years across. Within this image, you can see individual stars, over 100 million of them. You can see star clusters, nebulae, dust lanes, all in exquisite detail. The image is so detailed that if you were to print it at typical photograph resolution, it would be about 150 feet long. That's longer than an Olympic-sized swimming pool. The level of detail is staggering. You can zoom in on individual star-forming regions and see the structures within them. You can identify different types of stars based on their color and brightness. You can trace the spiral arms, see how the dust lanes thread through them, and observe how the structure varies from the inner regions to the outer disk. The Spitzer Space Telescope, which operated in infrared wavelengths, has also studied Andromeda extensively. Infrared observations are particularly valuable because they can penetrate dust that blocks visible light. This allows astronomers to study regions of the galaxy that are hidden from visible light telescopes. Spitzer's observations have revealed the distribution of dust throughout Andromeda, shown where star formation is occurring even in dusty, obscured regions, and provided insights into the galaxy's thermal structure. The Chandra X-ray Observatory has studied the high-energy universe, including Andromeda. Chandra's observations have identified hundreds of X-ray sources in Andromeda, including supernova remnants, binary star systems, and the faint emission from the central supermassive black hole. These observations help astronomers understand the most energetic processes occurring in the galaxy. Radio telescopes have mapped the distribution of hydrogen gas in Andromeda. This gas, which is invisible to optical telescopes, is the raw material for future star formation. By studying where the gas is concentrated and how it's moving, astronomers can predict where new stars will form in the future. Radio observations also reveal the galaxy's rotation curve, providing crucial evidence for dark matter. And in the future, even more powerful telescopes will study Andromeda. The James Webb Space Telescope, which launched in 2021, is already beginning to observe Andromeda in unprecedented detail in infrared wavelengths. Webb's infrared capabilities will allow it to see even deeper into dusty regions, revealing star formation happening in environments too obscured for even Hubble to observe. The Vera C. Rubin Observatory, currently under construction in Chile, will conduct the largest survey of the night sky ever attempted. It will repeatedly image the entire visible sky, creating a time-lapse of the universe. Andromeda will be one of the objects studied in detail, with millions of observations tracking changes over time. And the next generation of extremely large telescopes, the Extremely Large Telescope, the 30-meter telescope, and the Giant Magellan Telescope, all currently under construction, will have the light-gathering power to study individual stars in Andromeda in even greater detail than Hubble. These telescopes will allow astronomers to study stellar populations, measure the properties of individual bright stars, and potentially even detect exoplanets in Andromeda, though that remains a significant technical challenge. The point is, our understanding of Andromeda continues to grow. Every new telescope, every new instrument, reveals something we didn't know before. And as our technology improves, so does our ability to study this magnificent galaxy. Let's talk about the philosophical implications of Andromeda's scale. When you really grasp how enormous Andromeda is, how distant, how filled with stars and potential worlds, it changes your perspective. You realize that Earth is not just small, it's infinitesimally small. We're a tiny speck orbiting an ordinary star in an ordinary galaxy, and Andromeda is another galaxy, just as large, just as full of potential, sitting across the cosmic void. If there's life in Andromeda, and statistically there almost certainly is, those beings are looking up at their night sky just as we look up at ours. They're asking the same questions. Where did we come from? Are we alone? What is the universe? They might have developed their own science, their own technology, their own civilization. They might be far more advanced than us, or far less advanced. They might have built telescopes and observed the Milky Way, seeing it as we see Andromeda, a faint smudge in their night sky. They might have figured out that the Milky Way is approaching them, that a collision is inevitable billions of years in the future. They might be planning for it, thinking about how their descendants will navigate the merger, or they might not exist at all. They might have existed in the past and gone extinct, or they might not have evolved yet. Given the vast timescales involved, the odds that any hypothetical civilization in Andromeda exists at exactly the same time as us are quite small. The universe is about 13.8 billion years old. Human civilization is only a few thousand years old. Technological civilization, the kind that builds telescopes and spacecraft, is only a couple hundred years old for us. If a civilization in Andromeda existed 2 million years ago, we'd never know. Their signals, if they sent any, would only now be reaching us, and they'd be incredibly faint and difficult to detect, and they might have long since gone extinct, leaving no trace except perhaps some ancient ruins on a planet we'll never be able to observe directly. Conversely, if a civilization arises in Andromeda 1 million years from now, we'll never interact with them. The signals we're sending out now, our radio and television broadcasts, will reach Andromeda in about 2.5 million years. By that time, humanity might not even exist anymore. We might have evolved into something unrecognizable, or we might have gone extinct, or we might have spread throughout the galaxy and beyond, becoming something far greater than we are now. The point is, space is not just big in terms of distance, it's big in terms of time. The cosmic timescales are so vast that even if intelligent life is common in the universe, the probability of two civilizations existing at the same time and close enough to communicate is quite small. We might be alone, not because life is rare, but because we're separated from other life by vast gulfs of space and time. Or we might have neighbors, civilizations in Andromeda or other galaxies, but we'll never know because the distances are too great and the signals too faint. These are questions we can't answer with current technology, but they're worth thinking about because they put our existence in perspective. We're part of something much larger than ourselves, a universe filled with galaxies and stars and potentially countless worlds. And Andromeda, hanging in our night sky, is a reminder of that larger reality. It's a reminder that we're not alone in the universe, or if we are, it's a universe so large that even being alone doesn't diminish the wonder of it. Let's talk about one more aspect of Andromeda's scale that I haven't covered yet: the timescales involved. We've talked about distances, about the number of stars, about masses and sizes, but time is just as important. Andromeda formed about 10 billion years ago. The universe is 13.8 billion years old, so Andromeda has existed for about 70% of cosmic history. During that time, the galaxy has evolved enormously. It started as a cloud of gas in the early universe, probably not much different from any other gas cloud at the time. But as gravity pulled the gas together, as stars began to form, as the galaxy's structure developed, Andromeda became what it is today. This took billions of years. Billions. To put this in perspective, Earth formed about 4.5 billion years ago, so Andromeda is more than twice as old as our planet. Andromeda existed before our solar system was even a gleam in a molecular cloud's eye. Stars were being born and dying in Andromeda for billions of years before the Sun even existed. Think about that. While Andromeda was already a mature galaxy with hundreds of billions of stars, the region where our solar system would eventually form was just part of the Milky Way's diffuse gas. No sun, no Earth, no life. Just gas and dust drifting through space. And Andromeda will continue to exist long after our current era. The collision with the Milky Way, which seems like such a dramatic event to us, is just one moment in the galaxy's long history. Andromeda has probably collided with other galaxies before. We know it's consumed multiple dwarf galaxies. There might have been larger mergers in its past as well. And after the merger with the Milky Way, after Milkomeda forms, that galaxy will continue to exist for trillions of years more. Long after all the stars that exist today have died, new stars will still be forming in Milkomeda, at least for a while. Eventually, the gas will be used up and star formation will cease. Then Milkomeda will become a dead galaxy, filled with old, dim stars, slowly fading as those stars die one by one. The last stars to die will be small red dwarfs, stars with only a tenth or less the mass of the Sun. These stars burn their fuel so slowly that they can live for trillions of years. The universe isn't old enough yet for any red dwarfs to have died of old age. Even the oldest red dwarfs, formed shortly after the Big Bang, are still burning. So Milkomeda will continue to shine for trillions of years, slowly dimming as more and more stars die and are not replaced by new ones. Eventually, maybe 10 trillion years from now, the last stars will die. Milkomeda will become a dark galaxy, filled with stellar remnants, white dwarfs, neutron stars, black holes, all that will remain of the once magnificent galaxies that merged to create it. But even then, even after all the stars are dead, Milkomeda will still exist. The stellar remnants will still be there, still orbiting the central supermassive black hole. And on timescales so long they're almost incomprehensible, even these remnants will eventually disappear. Protons, the particles that make up atomic nuclei, might decay into lighter particles. This is a hypothetical process that hasn't been observed, but some theories of particle physics predict it will happen given enough time. If proton decay occurs, white dwarfs and neutron stars will gradually evaporate, their matter converting into radiation and lighter particles. Black holes will evaporate through a process called Hawking radiation, slowly losing mass and energy until they finally disappear in a final flash of radiation. This process takes an unimaginably long time. A black hole with the mass of the Sun would take about 10 to the 67 years to evaporate. That's 10 followed by 67 zeros, years. For comparison, the current age of the universe is only about 10 to the 10th years. About 10 billion years. The time for a black hole to evaporate is 10 to the 57 times longer than the current age of the universe. It's a number so large, it's essentially meaningless. So on the longest timescales, even black holes will disappear. Eventually, all that will remain of Milkomeda and of every other galaxy will be a diffuse sea of radiation and elementary particles. The universe will have reached a state called heat death, where everything is at the same temperature and no useful energy remains to do work. This is the ultimate fate of the universe, according to our current understanding of physics. But that's trillions upon trillions of years in the future, so far ahead that it's almost absurd to think about. For now, for the next hundreds of billions of years at least, galaxies like Andromeda will continue to shine, continue to form stars, continue to be magnificent structures in an evolving universe. Now, let's come back to the present and talk about what Andromeda means for us today. As I said at the beginning, Andromeda is visible to the naked eye if you know where to look. On a clear, dark night, away from city lights. You can see it as a faint smudge in the constellation Andromeda. That smudge is a galaxy containing 1 trillion stars. 1 trillion. A number so large, it's almost incomprehensible. And that galaxy is 2.5 million light-years away, meaning the light you're seeing left Andromeda before humans even existed. When you look at Andromeda, you're not just looking at a distant object, you're looking back in time. You're seeing Andromeda as it was 2.5 million years ago. If someone in Andromeda were looking at the Milky Way right now, they would see it as it was 2.5 million years ago. They would see a galaxy before humans existed, before civilization, before technology. Just a galaxy full of stars, slowly rotating, forming new stars, consuming smaller galaxies, doing what galaxies do. And billions of years from now, assuming humans or our descendants still exist, they'll look up and see something different. They'll see Andromeda and the Milky Way in the process of merging, 2 galaxies becoming one. They'll see a night sky filled with stars from both galaxies, a spectacular light show that will last for billions of years. And eventually, they'll see the merged galaxy, Milky-Way, a single large elliptical containing all the stars from both parent galaxies. That's our future, assuming we survive that long. But for now, Andromeda is a separate galaxy, distinct from our own. A magnificent structure, 220,000 light-years across, containing 1 trillion stars, held together by gravity and dark matter. It's approaching us at 250,000 miles per hour, but it won't arrive for another 4 billion years. We have time to explore our own galaxy, time to develop new technologies, time to spread beyond Earth if we choose to, time to build civilizations, to create art, to make discoveries, to live our lives. And through it all, Andromeda will be there, hanging in the night sky, a reminder of the vastness and beauty of the universe. So when you look up tonight, find Andromeda if you can. It's in the constellation Andromeda, not hard to find if you're in a dark location. Look for the faint smudge of light, and remember what you're seeing. You're seeing a galaxy containing 1 trillion stars, each one potentially with its own planets, its own moons, its own unique characteristics. You're seeing light that has traveled for 2.5 million years to reach your eyes. You're seeing a structure 220,000 light-years across, so large that light takes that long just to cross it. You're seeing our closest large galactic neighbor, our future partner in a cosmic merger that will reshape both galaxies, and you're seeing proof that the universe is far larger, far more complex, far more wonderful than we can fully comprehend. That's the true scale of the Andromeda Galaxy. A scale that encompasses not just enormous distances and unimaginable numbers of stars, but also deep time, cosmic evolution, and the ongoing story of structure formation in an expanding universe. Andromeda is more than just a galaxy. It's a window into understanding how galaxies form, how they evolve, how they interact with each other. It's a laboratory for studying stellar populations, star formation, supermassive black holes, dark matter, and countless other phenomena. It's a mirror that shows us what the Milky Way might look like from the outside. And it's a reminder of our place in the cosmos. We're tiny, yes, insignificant on galactic scales, certainly, but we're also capable of understanding. We can look at Andromeda, 2.5 million light-years away, and figure out how far it is, how big it is, how massive it is, what it's made of, where it came from, and where it's going. That ability, the ability to comprehend the universe despite our smallness, is what makes us remarkable. It's what makes science valuable, and it's what makes studying objects like Andromeda worthwhile. Because every time we learn something new about Andromeda, we learn something new about the universe. We learn about the laws of physics that govern everything. We learn about the processes that formed galaxies and stars and planets. We learn about the history of the cosmos and its future, and we learn about ourselves, about our place in this vast, ancient, magnificent universe. So thank you for joining me on this journey through space and time. Thank you for taking the time to think about something as enormous and distant as the Andromeda Galaxy. And thank you for being curious, for wanting to understand, for looking up at the night sky and wondering what's out there. The universe is vast and beautiful and strange. Andromeda is just one galaxy among billions or trillions. But it's our neighbor, our future partner, and a magnificent example of what the universe can create given enough time and enough matter. Keep looking up. Keep asking questions. Keep exploring. Because there's always more to discover, always more to understand, always more wonder waiting to be found. The true scale of Andromeda isn't just about numbers and distances, it's about perspective. It's about understanding that we're part of something much larger than ourselves. It's about recognizing that the universe is more magnificent than we ever imagined. And it's about never stopping our quest to understand it all. That's what Andromeda teaches us. And that's why it's worth studying, worth thinking about, worth looking at on a clear, dark night. Because in that faint smudge of light, there's an entire galaxy. 1 trillion stars, countless worlds, billions of years of history, and a future collision that will reshape everything. That's the true scale of the Andromeda Galaxy, and it's absolutely magnificent. We've mapped its structure in incredible detail. We've studied its stellar populations, its gas clouds, its dust lanes. We've measured its mass, its size, its rotation. We've discovered its satellite galaxies and tracked their orbits. We've observed star formation happening in real time, watching new stars being born in Andromeda's spiral arms. We've even detected X-rays from Andromeda, emitted by hot gas and by objects like neutron stars and black holes. Modern telescopes can observe Andromeda across the entire electromagnetic spectrum, from radio waves to gamma rays. Each wavelength reveals different aspects of the galaxy. Radio observations show the distribution of cold gas, the raw material for star formation. Infrared observations penetrate the dust, revealing stars hidden from visible light. Ultraviolet observations highlight the hottest, youngest stars. X-ray observations reveal high-energy phenomena like supernovae remnants and accreting black holes. All of this data has built up a comprehensive picture of Andromeda as a complex, dynamic, evolving system. It's not just a static collection of stars. It's a living, breathing entity, constantly changing, constantly evolving. Now, let's bring this all back to the original question. What is the true scale of Andromeda? We've talked about numbers: 220,000 light-years in diameter, 1 trillion stars, 1.5 trillion solar masses, 2.5 million light-years away. But numbers alone don't capture the scale. To really understand the scale of Andromeda, you need to grasp what these numbers mean. Think about this. If you could travel at the speed of light, the fastest speed possible, it would take you 220,000 years to cross Andromeda from one side to the other. 220,000 years. Humans have only existed for about 300,000 years. Written history goes back only about 5,000 years. The entire span of human civilization, everything we've built, everything we've accomplished, all of recorded history, is just a tiny fraction of the time it would take light to cross Andromeda. And remember, this is at the speed of light. If you were traveling at the speed of our fastest spacecraft, crossing Andromeda would take trillions of years. Or think about the number of stars: 1 trillion. If every person currently alive on Earth were to study one star for their entire life, we'd only cover about 8 billion stars. We'd need about 125 civilizations like ours, all working together to assign one star to each person. And that's assuming everyone dedicates their entire life to studying a single star. Or think about the distance. 2.5 million light-years. The light you see when you look at Andromeda left that galaxy 2.5 million years ago. At that time, the earliest human ancestors were just beginning to appear. Homo habilis, one of the first members of the genus Homo, was using primitive stone tools. There were no cities, no writing, no agriculture, no art, no music, no civilization. Just small groups of early humans surviving in the African savanna. And over the next 2.5 million years, as that light traveled through space toward Earth, humanity evolved. We developed language, culture, technology. We spread across the globe. We built cities, civilizations, empires. We invented writing, mathematics, science. We split the atom, decoded DNA, landed on the moon. All of this happened during the time it took light from Andromeda to reach us. That's the scale we're talking about. Distances so vast that light, traveling at 186,000 miles per second, takes millions of years to cross them. Structures so massive that they contain trillions of stars, each one a sun, many with their own planetary systems. Galaxies so large that crossing them at the speed of light would take longer than all of human history. This is the true scale of Andromeda, and here's what makes it even more mind-bending. Andromeda isn't special, it's just a galaxy. One galaxy among billions, maybe trillions, in the observable universe. There are galaxies much larger than Andromeda. IC 1010-1, which I mentioned earlier, is about 27 times wider and contains 100 times more stars. And IC 1010-1 isn't even the largest galaxy we've discovered. There are others. And beyond the galaxies we can see, beyond the edge of the observable universe, there are probably countless more galaxies that we'll never be able to observe because their light hasn't had time to reach us yet. The universe is so incomprehensibly vast that even something as enormous as Andromeda is just a tiny speck in the grand scheme of things. And Earth, our home, is so unimaginably small compared to Andromeda that it defies description. If Andromeda were the size of the United States, Earth would be smaller than a single atom, much smaller. In fact, you couldn't even see Earth at that scale. It would be invisible, lost in the vastness of space. That's how small we are. That's how big the universe is. But here's the beautiful thing. Despite our smallness, despite the incomprehensible scale of the universe, we can understand it. We can measure it. We can study Andromeda, 2.5 million light-years away, and figure out how many stars it has, how massive it is, how fast it's moving. We can predict that it will collide with our galaxy in 4 billion years. We can understand the physics that governs its formation and evolution. We're tiny, yes. Insignificant on cosmic scales, yes. But we're also curious, intelligent, capable of understanding the universe we live in, and that, in itself, is remarkable. We're made of atoms that were forged in the cores of dying stars billions of years ago. We're literally made of stardust, and those atoms, organized into the complex structures that make up our bodies and brains, can look up at the night sky, see a faint smudge of light, and understand that it's another galaxy, 2.5 million light-years away, containing 1 trillion stars, on a collision course with our own galaxy. That's the miracle of human intelligence. That's the power of science. We can comprehend scales far beyond our everyday experience, understand processes that take billions of years, and make sense of a universe that is vast beyond imagination. So when you look at Andromeda tonight, when you see that faint smudge in the constellation Andromeda, remember what you're looking at. You're seeing light that has traveled for 2.5 million years to reach your eyes. You're seeing a galaxy containing 1 trillion stars, each one a sun, many with their own worlds, You're seeing a structure 220,000 light-years across, held together by gravity and dark matter. You're seeing our closest large galactic neighbor approaching us at 250,000 miles per hour for an inevitable collision billions of years from now. And you're seeing proof that the universe is far larger, far more complex, and far more wondrous than we could ever have imagined. That's the true scale of the Andromeda Galaxy. And it's just one galaxy among countless others in an infinite cosmos. Thanks for staying with me through this journey across space and time. The universe is vast and beautiful and strange, and I hope I've given you a new appreciation for just how incredible it all is. Keep looking up, keep asking questions, and keep exploring the depths of space. There's always more to discover.